Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is Introduction to Reciprocating Compressor. This is the 29th module of the course Thermodynamics and its Application. I am Subhasis Maji, Professor in School of Engineering and Technology from Indira Gandhi National Open University. Today's topic is Introduction to Reciprocating Compressor. After listening to this video lecture, you will be able to understand the concept of reciprocating compressor. You will be able to know the compression process. You will be able to explain the compression in steady flow. You will be able to describe the efficiency of a compressor. You will be able to discuss the compression work by reciprocating compressor, and you will be able to solve the numerical related to reciprocating compressor. Let us begin our discussion. Compression of gases is an important process in many power plants, refrigerant plants and industrial plants. Industrial uses of gas compression occurs in connection with pneumatic tools, air brakes for vehicles, servo mechanisms, metallurgical and chemical process, conveying of materials through ducts, production of bottled gases and transportation of natural gas. The term gas compression applies only to process involving appreciable change of gas density. This excludes ordinary ventilation and furnace draft processes. Now let us first discuss the basic terms related to reciprocating compressor. Bore, that is cylinder diameter. Stroke, that is distance through which the piston moves. The two extreme points of the piston are known as head end and crank end dead. The clearance volume, volume occupied by the fluid when the piston is at head end dead center. Piston displacement, in short form we write PD, that is volume a piston sweeps through. Compression ratio, ratio of cylinder volume with the piston at a crank end dead center to the cylinder volume with the piston at head end dead center. Single acting, where only one side of the piston is used. Double acting, where both the sides of the piston are used. Now we will discuss about the volumetric efficiency of a compressor. Volumetric efficiency is a measure of the effectiveness of the machine with regard to gas handling. So, volumetric efficiency is equal to volume of gas actually compressed and delivered as measured at inlet pressure and temperature divided by piston displacement. We can also define the volumetric efficiency of a reciprocating compressor as mass of gas actually compressed and delivered divided by mass of gas occupying the piston displacement at inlet pressure and temperature. Let us discuss about the compression process. A gas compression process may be designed either to the adiabatic or to involve heat transfer, depending on the process for which the gas is compressed. If the compressed gas is to be used promptly in an engine or in a combustion chamber, adiabatic compression may be desirable in order to obtain the maximum possible energy in the gas at the end of completion. In many applications, however, the gas is not used promptly but is stored in a tank for use as needed. You might have heard about the use of compressor. The compressors are used in refrigeration cycle. Compressors are also being used in heat engine, and we will discuss about the process which is going on inside the compressor, how we can calculate the work done, how we can calculate the efficiency of a compressor. Now we shall discuss about the compressor for which the gas is not being used promptly. At a later time, generally we use the compressed gas. The gas in the tank loses heat to the surroundings and reaches room temperature when finally used. In this case, the overall effect of compression and storage is simply to increase the pressure of the gas without change of temperature. It can be shown that if the gas is cooled during compression instead of after the process, the work required will be less than for adiabatic compression. A further advantage of cooling is the reduction of volume and the consequent reduction of pipeline losses. For this reason, since cooling during compression is not very effective, after coolers are often used to cool the gas leaving a compressor. In view of the fact of cooling on compression process, it is customary to investigate two particular idealized cases, namely reversible adiabatic and reversible isothermal, as well as a general case of reversible polytropic process whose equation is PV to the power n is equal to constant. The paths of these processes are plotted in figure 1. Now this is the figure 1 for reversible compression process. Now let us concentrate on the left hand side figure. The rightmost curve, which is indicated by PV to the power gamma is equal to constant, this is for the adiabatic process, and the process is going on from state 1 to the final state, that is state 2. And here the compression process is from initial pressure P1, that is denoted by state 1, to the final pressure at P2, which is denoted by 2. So PV to the power gamma is equal to constant represents the reversible adiabatic process. The next line, which is denoted by PV to the power n, is equal to constant. This curve represents the compression process related to polytropic process, and the line which is denoted by the equation T is equal to constant, that is the isothermal process. So this curve represents the compression process for an isothermal process, and you know very well that work done by any process can be found out by the area under the curve. From this figure, it is clearly visible that the area under the curve for the isothermal process is less. So work done for the compression process is less for isothermal process. Next, higher up work done is required for the curve which is represents by the polytropic expressions, that is PV to the power n is equal to constant, and the maximum work among these three processes is for adiabatic process, for which the curve is represented by the equations PV to the power gamma is constant. Now for all these three we have discussed so far is for PV diagram. Now if you look at the temperature entropy diagram, so you see that for the isentropic process the line is vertical, that is reversible adiabatic process the line is vertical, and for the isothermal process the line is horizontal. So for isothermal process the horizontal line is represented in the TS diagram, and the line which is in between the reversible adiabatic and isothermal process is for the polytropic process. So this is the diagram for reversible compression process. Now let us see how we can calculate the work of compression in steady flow. The steady flow energy equation per unit mass for a compression process is shown in figure 2. So figure 2 depicts the steady flow process. The steady flow energy equation per unit mass for a compression process is shown in figure 2, assuming that changes in potential and kinetic energy are negligible, may be written as Q minus Wx is equal to H2 minus H1. This equation is the flow equations for the steady flow process. So Q minus Wx is equal to del H is equal to H2 minus H1. This is equation number 1. Now if you see the block diagram here, you see that Q is the heat input for this compression process, and state 1 is the initial state whose enthalpy is H1, and state 2 is denoted by the point 2 for which the enthalpy is H2, and Wx is the work done. We also have the equations that is equal to TdS is equal to dH minus V dP. This we have elaborately explained in our earlier lecture, that is TdS is equal to dH minus V dP, and for a reversible process Q is equal to del H minus integral of V dP. Then for any of the idealized cases of figure 1 from equation 2 and 3, we can write Wx is equal to minus integral of V dP. For any gas, a compression process may be represented with sufficient accuracy by an equation such as PV to the power n is equal to constant. Now if you have the generalized equations, that is PV to the power n is equal to constant, so V you can write as P1 to the power 1 by n multiplied by V1 divided by P to the power 1 by n, because you know very well that PV to the power n is equal to constant. The constant you can write P1 V1 to the power n, and after doing some algebra you will get the final expression of V is equal to P1 whole to the power 1 by n multiplied by V1 divided by P to the power 1 by n. Now put this value of V in the expressions for work done Wx. So Wx is equal to minus P1 to the power 1 by n multiplied by V1 integral of dP 1 upon P to the power 1 by n. So if you perform the integrations for this expression for Wx, so finally you will get, after putting the upper limit and lower limit of the integrations, then Wx is equal to minus n divided by n minus 1 multiplied by P1 V1 within bracket P2 minus P1 whole to the power n minus 1 by n minus 1 bracket close. So this is the final expression for the work done for the polytropic process. So here n is the constant and P2 is the final pressure, P1 is the initial pressure, and V1 is the specific volume at the inlet of the compressor. Now once you have calculated for the work done for reversible polytropic process, there is no problem for calculating the work done for the reversible adiabatic process. Only in place of n you have to substitute gamma because rest of the procedure are identical. The work of the compression or the steady flow work input to the gas is the negative of the shaft work Wx. Therefore, Wn we can calculate, that is equal to n whole divided by n minus 1 P1 V1 within bracket P2 by P1 whole to the power n minus 1 by n minus 1 bracket close. But here we just omit the minus sign because the work done for the work is negative of the work, that is Wh. So W gamma is equal to work of reversible adiabatic compression. As I already told you, for this case only you have to substitute gamma for n. So W gamma is equal to gamma divided by gamma minus 1 P1 V1 multiplied by P2 by P1 whole to the power gamma minus 1 by gamma minus 1. That is equation number 6. Now we will calculate the work done for the isothermal process. For isothermal compression of a perfect gas, that is PV is equal to constant, the work of reversible isothermal compression, that is equal to Wt is equal to minus Wx is equal to P1 V1 integral of dP by P. This is a simple integrations. If you perform the integrations and putting the upper limit and lower limit, you will get the final expression for Wt is equal to P1 V1 ln P2 by P1. Now let us find out what will be the expression for the work done for isothermal compression. For isothermal compression of a perfect gas, that is PV is equal to constant, the work of reversible isothermal compression, that is Wt is equal to minus Wx is equal to P1 V1 integral of dP by P. This is a simple integrations. You can calculate the final work done, that will be equal to P1 V1 ln P2 by P1. In the PV plot of figure 1, the work of compression for each type of process is represented by the area between the path of that process and the axis of pressure. It is evident that the work of reversible isothermal compression is less than the work of reversible adiabatic compression. The work of reversible polytropic compression is intermediate between the others if n lies between gamma and unity. This is the case in reality, as the polytropic case will involve some cooling but not enough to obtain isothermal compression. In a real compressor, the work will be greater than the work of the reversible compression process because of friction. In such cases, the path of compression may be represented by PV to the power n is equal to constant, but the work of compression is not given by integral of V dP. The shaft work cannot be determined solely from the properties of the fluid. The frictional effects in a reciprocating compressor are often small, so that the work may be computed by the integral of V dP without great error. The efficiency of a compressor working in a steady flow process may be defined as eta C adiabatic is equal to H2S minus H1 divided by WC, or equal to W gamma by WC, where WC is equal to shaft work supplied to the actual compressor per kg of gas passing through. W gamma is equal to shaft work supplied to a reversible adiabatic compressor per kg of gas compressed from the same initial state to the same final pressure as in the actual compression. The above efficiency is generally referred to as the adiabatic efficiency. If the desirable idealized process is taken to be the reversible isothermal process, then the compressor efficiency is called the isothermal efficiency. So eta C isothermal is equal to Wt by Wc, where Wt is equal to shaft work supplied to reversible isothermal compressor for compressing 1 kg of gas from the same initial state to the actual final pressure. The normal thermodynamic practice is to use the reversible adiabatic gases. Because of the fact of cooling, the adiabatic efficiency of a real compressor may be greater than unity. Many turbine type compressors are essentially adiabatic machines, and for these machines the work of compression WC is equal to H2 minus H1, where H1 is the enthalpy at state 1 and H2 is the enthalpy of the gas at state 2. Then for an adiabatic compressor, the efficiency is eta C is equal to H2S minus H1 divided by H2 minus H1. Dear students, we have discussed about the compressor work, how to calculate the compressor work for the polytropic process, for the adiabatic process, and also for the isothermal process. We have also discussed about how to calculate the efficiency. Now let us take some very interesting numerical so that your concept will be crystal clear. The first problem is compare the work per kg of air compressed from 100 kilopascal at 40 degrees centigrade to 600 kilopascal according to three processes: reversible adiabatic process, reversible isothermal process, and reversible polytropic process, which is given by PV to the power 1.3 is equal to constant. Now for the heat transfer from air, in each case the R is given as 0.287 kilojoule per kg and gamma is given as 1.4. For the first case, the expression for W adiabatic is given as gamma divided by gamma minus 1 P1 B1 multiplied by within bracket P2 by P1 whole to the power gamma minus 1 by gamma minus 1. And for this expression, since P1 B1 is equal to RT1 for the perfect gas equation, so we can write down the same expressions in this form, like W adiabatic is equal to gamma divided by gamma minus 1 RT1 multiplied by within bracket P2 by P1 to the power gamma minus 1 by gamma minus 1. So here gamma is given as 1.4 The value of R is given as 0.287 kilojoule per kgK. Temperature T1 is given as 313 Kelvin. P2 is given as 600 kilopascal. P1 is given as 100 kilopascal. Put the value and find out this. The value for W adiabatic, that comes out to be 210.19 kilojoule per kg. Next one is to calculate W polytropic process. Work done for the polytropic process. In the same way, we have to do it only. The value of N is given as 1.3, R value is given 0.287, T1 is same, P2, P1 are also given. There is no problem for calculating work done for the polytropic process. That comes out to be 199.33 kilojoule per kg. For the next case, P1 V1 is equal to RT1 for a perfect gas. For isothermal process, the expression for the work done is given as P1 V1 multiplied by ln P2 by P1, and W isothermal process is equal to RT1 ln P2 by P1. Here P1, P2, T1 and R are all given. There is no problem for us to calculate work done for the isothermal process. For this case, it comes out to be 160.95 kilojoule per kg. The next exercise, for the conditions given in exercise 1, find the adiabatic efficiency and the isothermal efficiency of the reversible polytropic compression. Now, we have already calculated the work done for the reversible adiabatic process. We have already calculated the work done for the reversible polytropic process. We have also calculated the reversible isothermal process. So, eta C isothermal is equal to WT by WC. WT and WC are all known. So, if you put the values, you will get the efficiency as 0.8075. In the next case, we have to calculate the efficiency for the adiabatic process. So, in this case, you have already calculated the work done for the reversible adiabatic process. You know WC, put the values of these two in the expressions for eta C adiabatic, and finally you will get 1.055. Dear students, we have already completed our today's discussion. Let us summarize our discussion very quickly. We have discussed the concept of reciprocating compressor. We have discussed the compression process. We have discussed the compression in steady flow. We have discussed the efficiency of compression for several processes. We have discussed the compression work by reciprocating compressor, and finally we have solved some interesting numerical on reciprocating compressor. Thank you very much.